Hello. So in the previous couple of videos we showed that Laplace gave us a way to go from calculus to algebra, and the way in which we could do that was we could say that, well, actually a capacitor is equivalent to 1 upon SC as far as the impedance is concerned. So what that means is wherever we see a capacitor inside a circuit, we can replace it with its general impedance, or this here. Okay, let's use that in anger now. So let's draw ourselves a circuit. So we've got an AC waveform. It's important it's AC for this application, as we discussed previously. Let's have a resistor R, and let's have a capacitor. Now obviously any measurements we're going to take are going to be here, but we're going to do that with a meter that has a very high impedance, so it might as well not be there, but this is where we're going to take our output voltage. Okay, you notice we haven't labelled this yet. We could label it. Okay, I'm going to label it here. So we've got R and C, an AC waveform. The amplitude is unimportant, but for those number people that can't handle doing things without numbers, if we say that's 5 volts peak to peak going in there, then everyone's happy, right? So now, does this remind you of anything? Well, actually, if we go back to a previous example, we saw a potential divider like this, if you remember. Like so. That was a potential divider, and we saw from the potential divider, and we derived the equation, V out is equal to V in R2 upon R1 plus R2. Can't remember that? Go back through the videos, it's there. And so we've got a way in which we can solve this one. Why can't we have a way in which we can solve the one on the left? Well, we can, because what I said to you earlier, and everything that this has been leading up to, is 1 upon SC is actually the impedance of the capacitor. It's a complex impedance, and it's been arrived at through taking the Laplace transform. But nevertheless, we can effectively, so we've got R here, we can effectively replace C with 1 upon SC, and that then corresponds to this equation here. So let's just put, instead of the C there, let's put 1 upon SC there. And now we can use this equation because we've effectively converted this to a resistor or its impedance. Its impedance is 1 upon SC. So what that means is now we have R1 is equal to R, and R2 is equal to 1 upon SC. Why? Because we're just potential divider equation. So the R1 is this one, and this one here is now R2. Okay, and R2 in our case is 1 upon SC because we've got a way in which we can replace the capacitor with an equivalent impedance. Okay, now comes the magic. So I'm going to use this equation here, but everywhere I see R2 I'm going to put 1 upon SC, and everywhere I see R1 I'm just going to put R. Okay, so I get this, V out is equal to V in, nothing different yet, R2, which is 1 upon SC, go with it, we don't mind top heavy fractions, that's absolutely fine in mathematics. We need to tidy them up afterwards, but they're okay at the moment. 1 upon SC upon R1, which is an R of course, R plus 1 upon SC. Okay, messy. I've seen tidier equations. Let's just move the camera across a little bit. What can we do with that? Well, of course we can tidy that up. because this 1 upon SC, this is actually on the bottom, of course. So what that means is V out is equal to V in 1 upon SCR, because we're multiplying through by the SC, so that's the SCR, and SC upon SC is 1. So V out equals V in 1 upon SCR plus 1, or in other words, the transfer function relating V out to V in, or V out divided by V in, the transfer function, what happens to the output compared to the input, we end up with 1 upon SCR plus 1. So what? So what? What good is that for anything at all? Well, that thing there tells me quite a lot of information, because C is constant. Unless I unsolder the capacitor and put a different one in. R is constant. Unless I unsolder the resistor and put another one in. So what I can say is actually that C and R I could just combine to be, so I could say C times R is just equal to, let's call it alpha. So what I end up with is 1 upon alpha S plus 1. Alright, I've got to take alpha and I've got to multiply with C, might be a microfarad, R might be 10,000 ohms or something. So I've got to calculate this, and that alpha is actually a time constant. But I've still got the basis of the equation, and I can use this basis of the equation to see how this circuit behaves. Now remember before I've said that S is actually pretty much equivalent to J omega, and omega is just 2 pi f, so it's really J 2 pi f. But everything aside, in other words, as I increase f, I'm going to increase s. So I can increase, what happens if I increase s? In other words, I increase the complex frequency. Well, let's look at it. So let's make s infinitely big. Infinitely big, what's infinitely big? Some would say 100, some would say 100 billion. I would say infinitely big was probably, you know, quite a big number is 1,000, right? It'd take you about 20 minutes to count to 1,000. So let's say infinitely big in this case is 1,000. So what we'll have in this case, if we say alpha is equal to 1, what we have here is 1 divided by 1,001. In other words, it's quite small. So as s gets big, the transfer function, V out over V in, the output sorry, I've done it again, I just need to cross a little bit. The output gets small. So as S gets big, the output gets big. As S goes, well, we'll do that in a minute, but as S gets big, the output gets small. As S gets small, well, what's the smallest number we know without going negative? Well, if we say S is equal to 0, then we have 1 upon 1. So as S gets small, output tends to 1. Interesting. Interesting. Because what it tells us that this circuit, as the frequency gets bigger and bigger, the output gets smaller and smaller. Let's plot a little graph of that if we've got room on this page. Yes, I think we have. So let's go for our little graph here. So if I say this is frequency, and I say that this is V out or V or output or anything you want to call it, what I see from this is S gets big, the output gets small. So in other words, as frequency gets big, the output gets small. So that puts me somewhere there on the graph. And this one down the bottom here tells me that as S gets small, the output tends to 1. So the V out here is just going to be here like 1, and I'm going to have a point somewhere here. So I've got a graph, and it's tempting just to draw a straight line across here and say that's it, that's the job done. So this circuit up here, what the circuit will do, it's obviously dependent on the size of the capacitor and the size of the resistor, but this circuit here is going to let low frequency through, because this is what this is here, low frequency through, and it's going to block high frequency. That's what it's saying. It lets the low frequency through and it blocks the high frequency. Now in actual fact the graph looks more like this because it's exponential, so that's what it actually looks like, but that doesn't really matter. We've got the two extremes that we're interested in. This circuit will pass low frequency and it will block high frequency. Now that's quite intuitive, because at high frequency, we saw from previous, this capacitor conducts, but at low frequency it doesn't. So what that means, at low frequency all of the voltage makes it to the V out, but at high frequency this point here is effectively conducted down to ground. So that's exactly what we see in this graph here. So we've gone from a circuit that would be very difficult to analyse because it would require some calculus, into something that we can just use standard numbers and representation on. We can do a bit of algebra, and now we can plot a graph that predicts how this circuit is going to behave. If we actually add in the R and the C values in there, in other words the time constant, we can even put values on this axis here as to actually what the frequencies are. That's not particularly important at this time, but we can do that. So we can predict with very, very great accuracy how this circuit is going to behave. Now this circuit here, so all the maths aside now, this circuit here is called a low pass filter because it passes low frequency and it blocks high frequency. Where would that be useful? A typical example would be talking into a telephone handset, because you don't want lots of high frequency hisses and squeaks, but you do want the low frequency of the human voice. So you could let the low frequency of the human voice through, but you could block the hisses and the squeaks and the high frequency noise. I think that's really clever. And obviously this is a very, very simple two-element circuit. The same principle applies whether we put inductors around here, capacitors around here, or whatever. We replace inductors with SL and we replace capacitors with 1 upon SC. So I'm just going to put a little crowning glory on here, and I'm going to call this a low pass filter. So that's the analytics for the low pass filter, and you can build low pass filters using inductors as well, or a combination of inductors and capacitors, but this is a low pass filter and it's of the kind just using an RC. Okay, it's first order because there's only one reactive device in there. So that's the magic of that. Okay, see you soon.